Basic probability. Lesson objectives: reduce probabilities written in fraction form, perform various operations involving probabilities, use tree diagrams to compute probabilities. Let's begin. Probabilities can be expressed as fractions, decimals, or percents. If you recall, probability is what we want divided by what we can get. So if we look at this example and we want to know what's the probability that a spinner will land in the green section, we first figure out what do we want. We want this 1/4 of this circle that is colored green. What can we get? We can get any of the 4 quarter sections. So the fraction for this probability of landing in the green spot would be 1 out of 4. The decimal, if you recall, to convert a fraction to a decimal, I take 1, I hit divide, and then I hit 4, and you should get 0.25. This is the same thing as saying 1/4 of a dollar. And then to convert this to a percent, I multiply it by 100 or simply move the decimal 2 places to the right and add a percent sign, 25%. Next, this one, if we count the sectors, there's 8. 3 of the 8 are green, so the probability that the spinner will land in the green section would be 3 out of 8. Decimal, 3 divided by 8 is 0.375, and the percent would be 37.5%. Next, here we have 1, 2, 3, 4, 5 triangles. They're all same area. 3 of the 5 are shaded purple. So the fraction for the spinner would be 3 out of 5. Decimal form, that would be 0.6. And to convert the decimal to a percent, I move the decimal 2 places to the right and add a percent sign. That is 60%. Whenever we express probability using fractions, we always want the fraction to be reduced. So how do we reduce? Well, we look for common factors that are in both the numerator and denominator, and the top number and on the bottom number. So if we look at this first example, we have 6 over 24. That is an even number over an even number. So whenever you have an even over an even, we know that 2 is a factor for both. So we can rewrite 6 and 24 as 2 times 3, that's 6. And in the denominator, 2 times what gives me 24? Well, that turns out to be 12. These 2's cancel, because we have one on the top, one on the bottom, and we get 3 over 12. But there is still another factor that are in both 3 and 12, and that turns out to be 3. So 3 times what gives me 3? Well, that's 3 times 1, and 3 times what gives me 12? Well, that's 3 times 4. The 3's cancel. I'm left with 1/4. Now we can skip this extra step by saying, oh, 2 goes into both these, but it turns out not only 2 but also 3, which tells us that 6 will go into both. So whenever you have a numerator and denominator, it's always good to check to see what is the largest factor. In this case, 6 is a factor of 6. Will 6 go into 24? And the answer is yes. So 6 divided by 6 is 1. 24 divided by 6 is 4. So 6 over 24 is the same thing as 1 over 4. Next we have 9 over 27. So in case you don't know this, if the sum of the digits adds up to be equal to a number that is divisible by 3, 3 will go into that number. So for example, 9, well, there's nothing to add 9. 3 will go into 9. But what about 27? Well, if I take 2 plus 7, I get 9, so that means 3 will go into 27. We can rewrite 9 over 27 as 3 times 3 over 3 times 9. The 3's cancel, and I'm left with 3 over 9. And of course, 3 over 9 can be reduced. 3 goes into 3, 3 goes into 9, and that reduces to 1/3. And again, if you use the trick, let's take the highest factor here in this numerator. In this case, it turns out to be 9. Is 9 a factor of 27? And the answer is yes. So this reduces to 1/3. So if we use that trick involving the 3, 2 plus 7 is 9, so 3 will go into 27. Will 3 go into 72? Well, 7 plus 2 is 9. 3 will go into 72 also. Now, will 27 go into 72? No, that doesn't work. But is there a higher factor than 3? It turns out that the same trick applies to 9. If you add up the digits, that number, if it's divisible by 9, 9 will go into the number. So 2 plus 7 is 9, 9 will go into 27, and 9 will also go into 72. 7 plus 2 is 9, so that means 9 will divide 72. So we can rewrite 27 over 72 as 9 times 3 over 9 times 8. The 9's cancel, and in reduced form we have 3 over 8. The only factors of 3 are 1 and 3, and those are not factors of 8, so it's reduced. Lesson objective. If we are adding or subtracting fractions, we must have a common denominator. In this case, we have 15 as a denominator, and all of the denominators are 15, so we can combine the numerators. So this becomes 2 plus 4 minus 1 all over 15. The denominator stays the same when we add or subtract. So this becomes 6 minus 1, which is 5. Bring over your common denominator, that's 15, and now we need to double check to make sure this doesn't reduce. 5 goes into 5. Will 5 go into 15? Yep. So this reduces to 1/3. For this problem, we have 1 minus 4/7. The denominator of this 1 is a 1. We need to change it to a 7, so we multiply the top and the bottom numbers by 7. So we get 7 over 7. 7 over 7 is the same thing as 1. 1 minus 4/7. Now that we have a common denominator of 7, we subtract the numerators, so we get 7 minus 4, and that's over 7, which gives us an answer of 3 over 7. So in statistics, we will use addition when we are finding compound probabilities involving 2 or more probabilities, and we will use subtraction when we use what's called the complement rule, where we do 1 minus a probability. For multiplication, when we're asked to find the probability of A and B happening at the same time, we will use the multiplication rule, so we have to know how to multiply fractions. Multiplying fractions is easier than addition or subtraction because we can multiply unlike denominators. So to multiply fractions, you simply take numerator times numerator over denominator times denominator. So 2/3 times 2/5 becomes 2 times 2 over 3 times 5, which is 4 over 15. There are no factors of 4, only 2 and 4, and that is not factors of 15, which are 3 and 5, not counting 1, of course. So this is reduced and we are done. If we are multiplying fractions with a whole number, we just put the whole number over 1 and we multiply. So this becomes 3 times 400 over 8 times 1, and that gives us 1200 over 8. And now the next step is to say, will 8 divide into 1200 evenly? And in this case it does, and we get an answer of 150. Technically we can say 150 over 1, but we can just say 150. This last example is using powers, so this is 1/3 to the 3rd power. So this means I take 1/3 and I multiply it by itself 3 times. Now we multiply the numerators, 1 times 1 times 1 over 3 times 3 times 3, and this becomes 1 because again we are multiplying, and this is not 9, we are not adding, we're multiplying. 3 times 3 times 3, which gives us 1 over 27. Lesson objective. A tree diagram is a visual way of writing the outcomes and the associated probabilities in an experiment. In this case, we are flipping a coin, and we can have an outcome of either heads or tails. And if the coin is fair, the probability of getting a heads is 1/2, 0.5, and tails is also 0.5. If I flip it one time, my outcomes are a head or a tail. Now if we flip the coin 2 times, if I flip the coin once, what are the outcomes? Well, that would be a head or a tail, and each of those have a probability of 0.5. But if I flip it again, then I have another branch off of each outcome. So if I flip the coin once and get a head, I can flip it again and get a head. So that gives me the outcome head on the first, head on the second, or I can get head on the first and tails on the second, and that's this outcome. Same way down here, the first flip is a tail. If the next flip is a head, I have tail and then a head, or I can flip and get a tail and then the second flip get another tail. So by flipping the coin twice, I get 4 different outcomes. Let's do our last example. A fair coin is flipped 3 times. Number 1, use a tree diagram to determine the sample space. The sample space is the list of all possible outcomes. Number 2, what is the probability of getting exactly 2 heads? And number 3, what is the probability of getting at least 1 head? So if you recall with probability, what we want for number 2, we want the outcomes that have exactly 2 heads. And what can we get? Well, that's the list of all possible outcomes. So let's start with number 1. Here's the tree diagram. Here is flipping the head 1 time, either heads or tails. And like the previous example before, if we flip it another time, we can either get heads or tails. Heads or tails. And if we flip it a 3rd time, we have another branch off of each outcome, which now gives us a total of 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 different outcomes for this event. These outcomes are the sample space. For number 2, what is the probability that we get exactly 2 heads? Well, this is 3. This outcome, we have a heads, and a tails. There's exactly 2 heads here. Same way with this one, we have 2 heads. This one only has 1. This one has 2. This one there's only 1. This one there's only 1, and this one we have 0. So the probability of getting exactly 2 heads would be, what do we want? We want any of these 3, so that's 3, over the total number of outcomes 8. So the probability is 3 out of 8. And number 3, we want at least 1 head. If you recall, at least 1 means I want 1 head, or 2, or all 3. Well, the first one we have 3 heads. That's definitely at least 1. Same way with the second outcome. This is 2 heads. Same way with the third. We have 2 heads, which is at least 1. And in this 4th outcome, we have exactly 1 head, so that counts. We have 2 here, that counts. We have 1 head here, that counts. And then we have 1 head here, and that counts. This one is all tails, so there's 0 heads. That is not at least 1 head. The probability of at least 1 head is 7 out of 8. Thanks for watching.